But first, before I start, I just want to acknowledge the traditional custodians of the land from which I'm broadcasting, the Darug people, and I want to pay my respects to their elders past, present, and emerging, and acknowledge that, you know, this country, this land has been a place of learning and sharing of knowledge for tens of thousands of years. So very lucky to be here. It's a great honor. And of course, I want to actually very genuinely extend my heartfelt thanks to AuScope, which is the government agency here in Australia that has generously been funding GPlates development since, I mean, as far as I can remember, since 2007, thereabouts. And it has built this open community software platform with lots of models that has evolved into servicing so many aspects of science, you know, from plate tectonics, geodynamics, very traditional stuff, to evolutionary biology, climate science, and, you know, more so now even data science, mineral exploration, and education, right? GPlates is used in high schools and universities and other places for teaching and outreach. I just want to take this opportunity as well to thank the amazing team of people supporting this workshop this week. Okay, so there's two components, which is GPlates and then the pyGPlates component, the Python API, if you want to call it that. So the first few days you're stuck with me, but thankfully Jono is around, who's a whiz, and he's going to be able to also help with any technical questions. Well, mainly troubleshooting, say, installations and so on. Hopefully we can make sure that everybody's got a working version of GPlates. It should be fairly easy to install, but there are some quirks of different operating systems that make it a little bit complicated in some cases, edge cases, thankfully. You know, if you make some fun screenshots or models, feel free to tweet us. You can see the Twitter handles here. I couldn't find Nicky or Chris on there, so I think Nicky and Chris.
I'll never be on Twitter.
Oh no, Nicky!
Very
come
against
on.
it. Sorry, guys.
Hey, Nicky, welcome. Great to see you. Okay, great. And yes, if you've got any questions as well, you know, feel free to email me. You've got my email. I've been sending you a few updates here and there, so feel free to email. Feel free to drop stuff in the chat. Yeah, we've got people from Toronto, Canada, from Portugal, Cape Town, Patagonia. I mean, this is just incredible. Hopefully it's not too late or too early for some of you. I did mention in one of the emails that I will plan on having another workshop that is more like friendly to the European and Asian time zones, and even New Zealand, right? It's probably quite early for New Zealand, so you can never make it perfect for everybody. So yeah, so this is kind of the rough schedule. I never really have a very rigid schedule because it depends on the audience, and the audience here, we have a very broad mix of people from different subdisciplines. We have people who are novice users, advanced users, intermediate users. So we'll adjust this as we go, and of course add any particular functionality anyone wants to explore as we go through as well. And I will share these slides as well as the PowerPoint slides. You might find some of the material useful for your own teaching. You know, as I think there's some really nice resources and animations that particularly other people have made. Now, most of you should have been able to download GPlates, so gplates.org. One of the new things that's happened is that we do ask for, say, your name and email. It is optional, but it's really just to highlight to AuScope, our funders, that there is a community that use GPlates. Because if we say there's only one or two people, you know, Sabin and Nicky and, you know, maybe Jono, using GPlates, they're not going to fund us. So if we can demonstrate broader community uptake, then that's always a good thing. And so I'll just jump out of PowerPoint and highlight some of this. Okay. So here's the GPlates website. You should be able to just go to download, and the two download options will take you to, well, downloading GPlates or pyGPlates. If I go to download GPlates, it'll take you to this page. One thing to keep in mind is that there's different installers. So for example, this is the Mac installer. This is the Windows-based installer. I can see it's a 64-bit installation. Some of you might have 32-bit laptops or machines, so you may get stuck there. So let us know if you have any issues. And then, of course, there's like, well, I mean, hundreds of flavors of Linux. We've stuck to, I guess, the main flavor, which is Ubuntu. So there should be everything up to the latest version that just came out like a couple of weeks back, the Jammy Jellyfish. And I did test it yesterday and it works fine. If you get really excited, you can compile it all from source. And, you know, Nicky has become the expert of compiling GPlates from source. And yeah, so essentially you don't have to fill in these fields, but I do recommend, you know, name, email, and just and it'll give you the download link. Okay, now then I do want to go through this link as well, just very briefly, which is the Earthbyte webpage and the resources. And the reason, oops, I think I need to update that link. But the reason why we can't ship all of the data that we have with GPlates is that the developers yell at me because, you know, I tried to bundle too many things in the geodata that comes with GPlates. So a lot of other resources you'll find on the Earthbyte resources tab. So if you go to data models and global and regional plate motion models here. So there's a bigger archive of plate tectonic reconstructions in here as well. Okay, so that's that, and I just need to get my Zoom panel out of the way. Okay, now there is also the user documentation is really handy. The user manual has had a major upgrade, and I really do recommend having a look through. And the GPlates tutorials are quite useful because they're focused really on case studies. So you can go through these at your own pace if you want to look at something in particular. So if you're looking at flow lines and motion paths, you'll be able to get some step-by-step instructions on that. So make sure you have a look at that. The last thing I wanted to show you was the GPlates forum, the discussion forum, and that can be quite useful. You can see that, well, someone's put in a post a few days ago. We need to get back to this person. But yeah, so that's one way to get some help. The benefit of the forum is that if you encounter a problem, it's likely that it will help other people as well as you know, when it's resolved. And yeah, so look, feel free to interrupt me at any time. Just yell out. This is meant to be very informal, and you know, it's meant to be focused on use cases that you might want to explore. So I don't want to dwell on this too much. Lots of downloads. Just for a few power users, the binaries and source code of GPlates will be moving to GitHub in the next few months. So just if anyone's really excited about that, you can keep that in mind. And it's used in lots of countries, lots of different settings. I mentioned that before. what's new in GPlates 2.3 is actually primarily lots of stuff under the hood. The compiling environment, the memory efficiency, and so on. One of the key improvements has been in the deforming reconstructions, being able to export the tectonic subsidence through time. Okay. So that's, just keep that in mind. And then for those of you who in the past had really a painful experience of installing GPlates on the Mac because it wasn't signed by, the Apple developer permissions, whatever, that's been fixed, and the Windows installers should be, I guess, trusted by Microsoft at this point, from what I remember. And that's just an example of the online resources. I'm not going to dwell on it. Okay, so the next 5 or so minutes, I just want to, rush through some slides to give people like a visual refresher on plate tectonic reconstructions, because they're used in lots of different ways in the biology, in the geodynamics, and so on. And I know that there's a lot of novice users, and there are people from other disciplines who don't really understand how these reconstructions are made. So these reconstructions allow us to restore the past position of continental blocks and ocean basins. And these can be applied to a whole range of applications. So, climate change, ocean circulation, resources, and evolutionary biology. Some of the key ingredients to the plate reconstructions are things like the tectonic fabric, particularly in the seafloor, like the fracture zones that have been mapped out by people like Marie Tharp, who was a pioneer, Cara Matthews, and others, which provide this essentially really important directional constraint of the relative plate motions. The other component that's really key is the age of the seafloor, right? You need to know how fast that seafloor spreading is occurring when it's happening. So this is a compilation from Maria Seaton from 2014, say 96,000 magnetic anomaly identifications. And I know Nicky Wright has been involved in this as well over the years. And lots of other people in the community, right? But these are key inputs to create the seafloor ages. And so when you combine these things, okay, so you've got your fracture zones. You can go out on ships and collect the seafloor ages, or the magnetic anomalies, interpret them along these profiles, and you can create these magnetic picks. And Nicky can tell you all about creating seafloor isochrons. And essentially what you can do then is undo that seafloor spreading, okay? And so this is an example for the Antarctica, Australia example. So there's the mid-ocean ridge, very young seafloor, and it gets progressively older. And with those two constraints, you can undo seafloor spreading. You can look at things like the spreading rates through time, the spreading directions, obliquities, and so on. So you can extract quite interesting kinematics. For me, one of the useful things has been looking at, the speed of the continents. If they've crashed into each other, they usually slow down. So the kinematics can be really useful indicators. Now, with the geodynamic models, for example, that we're interested in, we need to have a mantle or reference frame. We need to be able to use those relative plate motions, but then link it up to motions relative to the base of the mantle, essentially. And the most reliable way of doing that is using the hotspot tracks. I don't really want to dwell on that, but if anyone has any questions, I can elaborate. And there's different ways to look at this, whether you assume fixed or moving hotspots, and there's a whole bunch of papers on this sort of stuff. And this is just an example of one of these hotspot tracks, and you can combine them all globally and create this, what we call the hotspot reference frame. The hotspot tracks run out after about 100 million years, because seafloor has been consumed and that record of hotspot tracks becomes very difficult. And then we tend to rely a lot more on the paleomagnetic data to figure out, well, in most cases, the paleolatitudinal position of these continents. And of course, paleomag data is fantastic, but it has also some uncertainties in the paleolatitudes, whether it's inclination shallowing from compaction of the sediments. It can also be things like well, deformation, overprinting, and also the uncertainties of the age of the rock itself that you're taking the measurement from. So things can get a little bit more complicated. The only thing I would point out here is in a very purist way of thinking about it, there are different reference frames. There are the mantle reference frames that typically use hotspots or apply true polar wander corrections to the paleomag data, and we can discuss that maybe over the next few days. Okay, so there's the mantle reference frames, and then there's the pure paleomagnetic reference frames. Anyone working with climatically sensitive data should really think about this a little bit, and the preference is to use the pure paleomagnetic reference frames for anything that's climatically sensitive. So if you're looking at fossils and you want to look at their distribution relative to climate bands and so on, you should be looking at a paleomagnetic reference frame. Okay, so just keep that at the back of your mind, because we'll be talking about that throughout. Okay, and I think we can now jump into essentially getting stuck into GPlates. Does anyone have any questions at this point? No, all good. Okay, so for people on the Macs, the GPlates gets installed into applications. So if you just go to GPlates 2.3, double click, and you have GPlates that will open up. Okay, it will look like a very dull, boring gray screen. There's not much really there. On Windows, it should be added to your Windows menu, but it lives in program files, so just keep that in mind. And on the Linux machines, I mean, I can remote into my machine later if we want to check out the Linux option, but usually you just have to go to the terminal, type in GPlates and press enter. Okay, that's for the Linux machine. You can then keep that GPlates icon in the Linux dock, and then you can just launch it from there in the future. Okay, so just a little bit of a different way of accessing GPlates. While we're here, I do want to highlight that in most installations, wherever GPlates is installed, it comes with what we call a folder of geodata. And it's limited again because the developers yell at me for trying to cram in too many things, but there's a lot of useful things. So if you go to feature collections, there's everything from coastlines to igneous provinces to hotspots to flow lines and so on. Okay, paleogeography. I can see Marissa is here, so she might be interested in paleogeography, and we can go through that. So if to just get started very quickly with GPlates, for a novice user, this is what I suggest to students at high schools. You just open GPlates, you go to your geodata, and you go to the folder called Data Bundle for Novices. Okay, so hopefully some of you will be able to follow along. So again, that's in Applications, GPlates 2.3, Geodata, Data Bundle for Novices. And then something that's been introduced to GPlates in the last few years are what we call these GPlates project files. Anyone working with QGIS or ArcGIS knows those map documents, the MXD files and whatever. that don't contain any data, but they contain links to data. So you can essentially, in most cases, just click and drag that project file onto the GPlates globe. Okay. You won't get this window. This is just telling me that I have a few copies of this on my computer. And so that will take, the first time you load it, probably take about a minute to load. And you'll get something like this. So I'll give everybody a couple of minutes just to yeah, get going with that. Okay. So once you've got the globe up like this, you know, the default tool that's selected is this reorient globe tool. Okay, so you can just click and drag. You can use the left and right arrows up and down and move the globe around. Okay. Now, the exciting thing about GPlates is that you can, yeah, essentially use this time slider and reconstruct and understand and see what's happening in deep time. Okay, so you can use these controls, or you can just put in the numbers, say 250 million years ago, press enter, and you get a reconstruction. Okay, this particular model that is bundled with GPlates goes back to the Devonian, so it goes back to 10 million years ago. There are some alternative plate reconstructions in here, so I can very quickly show you in feature collections, alternative plate reconstructions, and there's the Meredith et al. 2021 Paleomag model that goes back to 1 billion years, and the Scotese Paleomap global plate model, which is for the whole Phanerozoic. So one of the reason why we have this one that goes back to the Devonian is that this is the model that we have that includes what we call deformation. So GPlates is essentially the first software to incorporate this evolving, deforming lithospheric model. You can see this this triangulation network here, and we'll talk more about the deforming stuff in the next couple of days. So Bruno says that the project doesn't open. Bruno, if you try instead going to File and then Open Project and then navigate to that folder, then that might work. If that doesn't work, I have seen some funny things with Windows, particularly if you have like lots of nested folders. You can kind of exceed the character limit for, you know, absolute paths, and it gets a little bit angry. So you can relocate that geodata folder, you know, to the C drive if you want, and that could fix it. Okay. So hopefully that helps. But yeah, so the other way of opening those project files is if you go to File and Open Project. Okay, so this is a very quick way of starting. To zoom in and out, you can just you can scroll with your mouse, or you can, you know, just drag this little slider, and if you get really excited, you can specify the zoom level down here. The other thing that you can do with a view, just to, you know, give you an idea of some basic interface tricks, is you can very easily change some of the common projections. So the 3D orthographic view can be really good if you're looking at a region, but if you want to have a global view, well, then you might want to have something like a Mollweide or Robinson projection. Okay. And there you go. Now, the default for the Robinson and Mollweide projections is this central meridian of 0 degrees, so Greenwich. But if you're like Nicky and you want to work on the Pacific, you can actually, well, change that central meridian very easily. So if you go to view, camera, sorry, set projection. So view, set projection, Robinson here, and we can just set it to the anti-meridian and have a Pacific viewpoint. Okay, has everyone managed to play around with that, follow that along? Any questions so far? No, everyone seems to be happy. Good. As you can see here, we have a bunch of layers, a bunch of data sets that we have preloaded in this project file. And I'll go through over the next couple of days of how you can bring in your own data and attach it to these plate reconstructions. And then we can also look at how you can maybe do some basic modifications of the plate reconstructions. We can also touch base on how you can actually create your own reconstructions from scratch. I mean, there's a whole community of world builders out there that don't want to use the plate reconstructions that are published, but actually want to build a whole model from scratch. So so we can go through that. Now, I wanted to just highlight this layers window because it's actually quite useful. Again, just some of the basics of you know, interacting with GPlates. And much like many GIS platforms, you have, well, lots of layers, and you can see this eye icon, and you can turn it on or off. So for example, if I turn this layer off, it will turn off the coastlines. Now, one of the things I wanted to just mention about the coastlines and what we've got here is the topography. And the topography is the present day topography. Okay, so this is not the paleotopography. There's a whole subdiscipline looking at paleo elevations, paleotopography, paleogeography. Okay, the reason why we often use coastlines and the present day topography in these visualizations is that it's just easy to track where your favorite region is going through time. Okay, because the coastlines have changed so much that it can be hard to keep track of where your samples might be. Okay, so you can turn layers on and off. You can, so let me just go back to those coastlines. We can expand the layers. So if I turn it back on, I can also fill the polygons. I can, if I click on this button called Set Draw Style, I'll be able to apply some different coloring. So I can apply different individual colors. Or I can color it, say, by the plate ID, which I'll talk about in a moment. Okay. So let's just, I'm just going to select one of these kind of extreme examples just to demonstrate the next thing, which is I can also change the opacity or the transparency of any layer here as well. Grace asks, how do we get the layer up? Yeah, this is a really good question because it can hide. So you should be able to go to Window up at the top and then Show Layers. So if you click on Show Layers, it'll appear. Sometimes it can get hidden behind lots of windows, and on Windows particularly, when you minimize it, it essentially hides in this weird corner on the screen. So hopefully that will help you find the catalog. Okay, now the question from Emily. The inactive deformation. So this is a really good question. At the moment, let me just go back to my orthographic view. we have two brown layers here, which are the deforming networks, right? There's the active deformation and the inactive deformation. Okay, so if I just have the active deformation, you can see that here in the mid-Cretaceous, this part of East Asia is actively deforming. If I zoom in, I'll be able to see some changes in the triangulation. I'll show you a trick now since we're looking at some details. GPlates is really awesome because you can very easily anchor a tectonic element and see what the relative motions might be around it. So to do that, you can try to memorize all the plate IDs. There's thousands of them, and I suspect that would be pretty hard. So let's not do that. What you can do is activate this selection tool, this little green Africa button, and say I want to keep this region fixed or anchored. So I can click on any one of these features and get, well, let's keep this fixed. And it has a plate ID of 619. And I'll talk about plate IDs a little bit later. So we can go to Reconstruction, specify anchored plate ID, type in 619, and click OK. Now, what you'll be able to see is that feature will remain fixed, and then everything will be moving relative to that feature. And the great thing here is that the GPlates is essentially on the fly calculating these relative plate motions. So it's very, it's nice and interactive that way, particularly if you want to look at a region of interest. Now, going back to the question of inactive and active deformation. In GPlates, what happens is, if I go back to the time of Pangea, so see, let me keep Africa fixed, which is 701. If I go back to say 200 million years ago, you see the opening of the Atlantic. You should be able to see some of this triangulation, okay? And this is what we call, well, that's the active deformation, okay? That's the active rifting that's happening. But then at some stage, we need to have a network of inactive deformation to take over. And that's a little bit of a detail, because what we'll talk about later is that you can drop a whole bunch of points, deform them in these networks. But if that network disappears, these points get left behind, right? They just get jettisoned. And so we need these inactive deforming points to bring them to the present day so that we can compare things like the crustal thicknesses and deformation. So Emily, I hope that answers your question. Okay. Now let's go back to the layers dialog, right? So we were looking at opacities. Here's the topography raster. Again, we can control the opacity, transparency of that here. The purple layers are special layers because they're actually what we call the plate topologies. And you can turn those off and you'll essentially see it looks more like a continental drift animation. And one of the biggest innovations in GPlates is having these continuously evolving plate boundaries and plates that we can interrogate. Okay, and tomorrow we'll go through some of the details of how to edit those and how to create your own topologies. So, Marissa, if you don't have those deforming layers, just make sure that you've got this data bundle for Novice from GPlates 2.3. If you're using an older version of GPlates, you might not have those deforming layers. And you may have loaded in a different project file, say from this alternative plate reconstructions from Meredith and SCRTs. So the Meredith model has no deformation in it. Okay, so it doesn't have those brown layers. And the SCRTs model doesn't have any deformation and doesn't have any plate boundaries either. Okay, so if I load in that, if I load in the SCRTs model, you see it just has the terrains. Now, you might be finding it hard to see some of the line thicknesses. GPlates doesn't have a lot of symbology control yet, because our funding has really been focused on scientific tools, right? Like those kinds of functionalities. But you can use some tricks. Like for example, if you go to Tools and then Configure Geometry Rendering, you can change the line width to be a bit thicker. So if I go 3, we'll be able to see that a little bit better. Okay. Same with the points. I know that on some of those very high resolution screens on Windows, the points can be tiny, almost invisible. And again, you can go to Tools, Configure Geometry Rendering, and change the point size hint to, I don't know, 8 or something like that. Okay, so that's just the SCRTs model. And again, I'm just demonstrating that you can easily drop those GPlates project files. I'll go back to the data bundle for Novice. And it will load in a minute. And we'll just have a little talk about the layers in terms of rearranging the layers. So for example, you can click and drag layers, and I've just put the layers the layer of topography up at the top, and you can see it essentially covers everything else. So that's something to look out for. Okay. The yellow layer is a special layer which doesn't actually have any geometry associated with it. It's what we call a rotation file. Okay. And in that rotation file is just a bunch of instructions on how to move each tectonic element. Now, keep in mind, we mentioned before that GPlates relies a lot on this thing called the plate IDs. So I suspect Nicky's favorite plate is the Pacific, so 901. Okay, and so GPlates has some instructions on how to move this plate, and that's recorded in what we call these Euler rotations. I'll talk about those again later. Let's not get bogged down into the details right now. Okay. And so yes, that yellow layer is the rotation file that contains those instructions. One of the things that GPlates allows you to do is to actually modify the reconstructions interactively, and you want to do this very carefully. You want to know what you're doing and why you're doing it. But for example, I can just grab one of these tectonic elements, one of these isochrons on the Pacific plate, click on Modify Reconstruction Pole, and I can just interactively move it, click Apply, click OK. And that can break a whole bunch of things, right? But it just highlights to you that, that you can, make edits on the fly and interactively. And yeah, Nicky would be probably quite unhappy to see me do that to the Pacific plate, because that would introduce all sorts of velocity artifacts. Now, if you've made some edits in GPlates and you're, not happy with them, unfortunately, there's no undo, redo. I mean, it's grayed out in most cases. In some places, in some instances, it is there. But in the case of what I just shown, you can go to this really important menu, which is the File and Manage Feature Collections. Okay, so I'll just show that again. So it's File and Manage Feature Collections. This window shows you all of the files that have been loaded. Okay, and it will show to you anything that's unsaved or has been modified. So for example, here, this red layer represents that modification that I just made interactively. I can choose to save that, but be very careful because that will then save that geodata, your master geodata model. You can, if you really wanted to mess around with it, you can create a duplicate of that geodata folder and these files. You can save as, and you can preserve those changes without messing up the originals. Okay, and in many cases, you just want to say reload, and so that will just undo any changes. If you don't want something in particular, so for example, if you don't want the topography raster, you can just click on unload and it will remove it. Okay, so this is a really useful little tool. One of my favorite things about it is that, for example, you've got these coastlines that we provide to you in this GPlates markup language compressed file, GPMLZ, right? But you might want to use it in ArcGIS, QGIS, and there's some rudimentary conversions that you can do here. So if you go to Save As, select the output folder, and you can output to say an Esri shapefile, OGR GMT file, or GeoJSON file. Okay, I know that these GeoJSON files are becoming more popular. So if I go back to that, here's that GeoJSON file that I've just created. And in most cases, GPlates will also happily read that GeoJSON or shapefile back in without a problem. Okay, so that just highlights to you some of the interoperabilities of GPlates with some of the common data and software formats. Okay, great. So let's just now, for the next 10 minutes before we have a quick break, let's just have a look at velocities, right? Relative and absolute plate velocities, because this is one of the most common things that people are interested in, right? And it's very easy to do. Now, you can hide certain things in your layers. Say you just want to look at the coastlines and the plate boundaries. You can click this hide all layers button at the top of the layers window. Okay. If you want to bring everything back, you can click show all. Okay, so if I hide all, and then I can re-enable just a few things, like the coastlines and the plate boundaries. And I'll just make these lines a bit thicker so we can actually see what's going on. Okay, so that's what I have. Now, in GPlates, I can generate a mesh of points to very easily interrogate the velocities. And this can be really useful because, you know, if you're starting to move blocks around and modifying your reconstructions, it should highlight to you if there's any major velocity artifacts that have been introduced. So to do that, you just need to go to Features and go to Generate Velocity Domain Points. There's a few different options. So there's some interoperability with some geodynamic mantle convection codes like SITCOM-S, Terra, but a lot of people are happy to just use the latitude longitude mesh. Now, I don't know if Ben is here right now, but it would be really cool to get the StriPy mesh in here, because that would be a really cool equal distance mesh. But let's just stick with a simple latitude longitude mesh. You can control the region. Let's just keep it global. You can control the
resolution by putting in, well, just playing around with these numbers, right? Just play around with these numbers, and you can see the resolution, the number of nodes that you'll get. Okay, so just put in 18 and 36, and select the output directory. I've just created a folder that I'm going to be using today, so I can easily delete it at the end. Okay, and you'll get something like this. Has everyone managed to get something like this with the velocities?
Yes.
Good. Excellent. Sophie wants me to go through that again. That's great. I always love the opportunity to have a look. So to demonstrate again, if I go to File, Manage Feature Collections, GPlates has loaded and created this new mesh. So I can just unload, so I can get rid of it. And so we can go to Features up at the top, Generate Velocity Domain Points, and go to latitude and longitude. And here you can mess around with the resolutions, right? You can get very excited about the resolutions, okay? And make sure that you set a target directory or an output directory here, okay? When you're ready, you can just click on OK, and you should get a mesh like this. Now, if it's a very high resolution mesh, GPlates will drop some of these arrows, just otherwise it would be impossible to see. And once you zoom in, you'll be able to see all of the arrows. Now, Chris asked, hey Chris, welcome. It's great to have you here. Chris asks, well, what are these velocities with respect to, right? And this is a really, really important question. They are with respect to the anchored plate. Now, if we go to Reconstruction and click on the specify anchored plate ID, the default is what we call the spin axis, right? It's what we would call the absolute reference frame, and you have to be careful in some of these plate reconstructions. You might have a plate ID that represents the mantle reference frame and a plate ID that represents the pure paleomagnetic reference frame, okay? So you can get complicated and quite fancy with this. So just keep that in mind. Now, if we are interested in just looking at Antarctica and Australia, again, we can inspect those plate IDs, but maybe we can have a quiz on plate IDs at the end of this, right? But Australia is 801 and Antarctica is 802, right? 802. So if I fix Antarctica, you'll see that all of these points within the Antarctic plate have no arrows, right? And what you should be able to see, if I go back to say 80 million years ago, is GPlates captures, the change in direction and speed of that rifting that progresses to slow seafloor spreading and then fast seafloor spreading. And what you'll notice is essentially that these arrows will, in most cases, align very nicely with, say the fracture zones, which are, just as a reminder, that directional constraint. So if I play that forward, you see Australia speeds up northwards at about 40 million years ago. And, maybe Chris or somebody else here can tell us why. It's not entirely clear yet to me why that happens. But one of the things that does happen is the Wharton Ridge gets abandoned, and perhaps there's more slab pull acting on the entire Indo-Australian plate from about 40 million years ago. But there's probably a paper or a couple of papers in there already. Okay, now Mohammed asks, can we filter those arrows? Now that's a really good question. You can do a few basic things with those arrows. You can I think you can mess around with the spacing. No, that doesn't. I've never really had to do that. So no, that doesn't look like it does it. You can definitely rescale the arrows, you know, if they're a little bit much, you can rescale the sizes, including the arrow heads, and so on. Okay. You can get fancy because in some of these geodynamic models, like the Terra models, I remember that if you have velocities that there's too much of a gradient at the plate boundaries, it can cause numerical instabilities. So you can smooth the boundary velocities, and you can. Okay, so this is really important in terms of velocity time stepping, right? It is interpolated. The velocities are interpolated in 1 million year intervals. You can choose to interpolate, say, at 5 million year intervals, but keep in mind that you'll apply some smoothing when you do that. And you know, the argument is always like, well, inherently in the magnetic peaks, you might have a resolution of only about 5 million years. So there's no point doing it at 1 million year intervals. The only reason I would say that you want to consider the 1 million year interval is that in the rotation file, there are changes in plate motions that are implemented. There's a whole hierarchy. You know, for example, in this case, Australia moves relative to Antarctica. Antarctica moves relative to Africa, and Africa moves relative to the spin axis. So if Africa moves, right, it has a knock-on effect on the absolute motions for Australia. Okay, but here we're just looking at the relative motions. Sorry if I've gone into a little bit too much technical detail here. I mean, while we're here, one of the things that you can do is by default, GPlates will attach these mesh velocities to just the topologies, right? The brown and purple layers, whether it's the deforming topologies or the rigid topologies. You can go and expand this light blue layer, this calculated velocity field, and remove the connection to the topologies, right? And instead, you can add, you know, say you're interested in what just the, you know, coastlines are doing, right? And so you'll get those velocities constrained. And I guess to answer Mohammed's question, you can filter and isolate those velocity fields that way as well by geometries. Okay. Gabriella is having some questions. Velocity interpolation options under long. You might need to make the window bigger. Sometimes these things get like hidden if the window is too small. And just make sure, yeah, that you've got GPlates 2.3 installed. Okay. What you might be looking at, Gabriella, is the green layer, that lat long velocity domain. Okay, so I suspect this is the confusion, right? Okay, excellent question. This is why these workshops are really good, because, you know, they highlight some common things that people come across and that I don't think about, you know, as often. But what GPlates creates is just a mesh of points, right? Equally spaced, at least in the degree space, okay? So it's just a bunch of points, but they have a special tag, you know, which is called mesh node, and that allows GPlates to extract the velocities, right? Now, what GPlates will do is create a separate blue layer with the same name, okay, in the layers field, which is the velocities. So you can essentially hide the velocity arrows, and you can separately hide the mesh nodes themselves. Okay, so you can just show the velocity, so it becomes a bit neater. So Gabrielle, I hope that answers your question. And then Mohammed asks, how can we fix the polar rotation for a specific plate? Yeah, so I, I, I think you're asking a very interesting question, which is a little bit more advanced. But for now, we're just let's just anchor individual plates instead. So we can very easily go specified anchored plate, go 101, and click OK. And so in some way, what this does is it imposes that North America will have an Euler rotation of 90 latitude, 0 longitude, and a rotation of 0. Okay, so whenever you anchor the plate, you are essentially fixing that Euler rotation of that plate, but allowing all the other components to move with respect to it. Yep. So Hojat asks a really good question about the features, right? The geometries, and this is a really good question. Let's come back to this question after a 5-minute break. I think it's good if everyone grabs a coffee or a drink or a toilet break. We'll come back to your question, Hojat. That's great. Excellent. All right. So see you in 5 minutes.
زیاتره خلکو چې کوم دی د اختر لا روزي له مور پلار راغوښتي لږ ولري
Okay. All right, so I assume a few people have come back. And so just to answer Hojat's question about, exporting, saving things out, what you can do is that you can save out these geometries. Now, you have to be quite aware of what GPlates does and how it works and how it thinks. The first thing to remember is that it stores everything in present day geometries. So like, anything coastlines or your fossils and so on, they are stored in the present day geometries. And in most cases, you're dealing with, just the WGS84 geographic coordinates. When you're dealing with things like the plate boundaries, it stores also all the plate boundaries throughout all time, right? So if you wanted to save out the plate boundaries at this snapshot, going to that manage feature collection and doing the save as won't work. And I'll talk about that because that's a separate functionality of exporting features. Okay, and now, but if we just look at those coastlines, well, you can very easily save as. And so, for example, if I want to save as, I can go to shapefile, save the shapefile. Okay, and I think you mentioned, Hojat mentioned rifts to have those names and attributes. Okay, now, if you're talking about the rifts that currently are implemented in GPlates, so if I just activate those deforming layers, okay, so these are well, in many cases they're inactive rifts, and there are some active deforming regions that say have compression and extension, but you can export the snapshots from here. Did someone want to jump in? No. Okay, so you can export the snapshot. So I'll show you how to do that because that may be a little bit more useful for you. So let me just demonstrate what I mean. So if I just open QGIS, and I need to update my QGIS because I think it was complaining about some plugin. So yeah, that's fine. Close. It's all good. So if I grab that shapefile that I've just saved out, okay, there is the shapefile of the coastlines, and this is in present day coordinates. That's what GPlates prefers to store and look at data that way. Okay, so that's the key thing, present day coordinates. Now, if you want to export the snapshots, you can go to Reconstruction up at the top. Okay, so Reconstruction and Export. And this is one of the more powerful menus within GPlates. Okay, I think it's really a good opportunity to talk about it. So there are two options. First of all, whether you want to export a whole sequence of snapshots or just a single snapshot at a particular time. But let's say I want to look at the the coastlines from 30 million years to 0 every 5 million years, right? So I can control that timing and the interval here. Be very careful because by default, it's like from 410 to 0 in 1 million year intervals, and you can generate really thousands of files. Okay, so just keep that in mind. So if I go to 30 to 0, 5 million year intervals, here is the export data type that I want. Currently it's blank, it's empty, but I can click on add export. And in most cases, well, I just want to export the reconstructed geometries. Okay, so just say the coastlines. And here I have a bunch of options to export in GMT, XY, ASCII files. And it gives me an option whether I want to compress, flatten all of the layers into one file or keep it as multiple layers. I can do the same for shapefiles. Okay, shapefile outputs, OGI, GMT, GeoJSON. Now keep in mind with the shapefile output, GPlates natively can actually store in one file points, polygons, and polylines. But when you export these snapshots, GPlates will have to split it into 3 different shapefiles, you know, because each shapefile can only contain, you know, points, multi-points, polylines, or polygons. But let's just assume, let me just click on shapefiles, click OK. And one of the key things is to make sure you change that target directory. So if I click on this little button here, specify the folder, click open, and click begin. Okay, so that will output a whole bunch of things. So these are the reconstructed geometries. And if I go to QGIS, and you can see they're coded by age. And you'll be able to notice that they're actually offset from one another. Now, again, keep in mind and be very careful with that the anchored plate ID. Okay, so if you are looking at the absolute motion of features, make sure you go back to plate ID of 0. Okay, if you're interested in just the relative positions between different plates, well, you choose which plate has to be fixed. So GPlates will export those values as you see them in GPlates. And while we're here, I also want to demonstrate, the velocity export, because that can be really, really useful. It's one thing to look at the velocities on the screen, but it's another thing being able to actually, quantify them and process them. So again, if you go to Reconstruction, Export, here we can actually just remove this layer. We don't want to export that anymore. We want to add an export for, in this case, velocities. Okay, so that's kind of halfway down this list. Okay. There's a bunch of options that you might not use. I mean, I can see there's a few users of SitcomS, so that you're probably already using it. Terra. The GPML plate velocities are pretty hard to read. And I always almost exclusively deal with these very simple text-based GMT XY velocities. Again, be very careful about the velocity time stepping. That's up to you, right? You can choose to export it to a single file for every 1 million year. And this is the most important thing, okay? This is the super, super important thing. The first option, the default option, is a Cartesian 3D vector. And I've never actually found this to be useful for any use cases. It's essentially how GPlates plots this thing on a 3D globe. Most of the times, and for any users of generic mapping tools, the most useful option here is the last one, which is the azimuth is reported 0 to 360 degrees clockwise from north, and 0 is north, and magnitude, which is the speed in centimeters per year. Now, I think Mohammed asked earlier about filtering. Here you can actually, print out every, say, 5th velocity node. If you have a very high resolution velocity, you can do some filtering here as well. You can also, multiply, scale those velocities if you're interested, but be careful with that. By default, most GMT data is presented as a longitude latitude coordinate first. So just keep that in mind. You can change that. And if you click OK and begin export, you'll get those velocities again at those times that you requested and in those intervals. If I go to 20 million years ago, and I just opened this in a simple text editor. Okay. This is the longitude, this is the latitude, and this is the azimuth, and this is the speed in centimeters a year. Now, that's because I'm just looking at the coastlines, but if I reconnect it all to the plate topologies, you'll see that all of those points will be fixed. So let me just see. Active deformation, plate boundaries. I'm not sure if I've done that correctly. Oh, whoops. I've completely screwed that up. These are the domains, the domain points. That's the green layer, and the surfaces is what I was looking for. Sorry. I want to add the purple and brown layers. Okay, and again, I can just go and redo that export. And you'll see that the velocities are global. So you can see, yeah, that's the mesh point. Okay, this is the azimuth, so the direction of that velocity. And this is the speed in centimeters a year. And what could be useful for many of you is also the plate ID, which is 101. I'm a little bit confused why there's plate IDs of 0, but I can investigate that. It's probably because I haven't connected up all the layers properly. Okay, any questions on some of those basic export functions? Yeah, so okay, so I'm just going through the chat. So Wenrong asks about the mid-ocean ridges through time. There is a layer. Have I closed my layers? No. So if I hide everything and just show the ridges, okay, this is just the ridges through time, okay? And so just the way I did that before, I can just go to export and make sure that I'm exporting the geometries, shapefiles. Okay, there's the ridges folder now, it's generated. And if we're looking at, this was at 30 million years ago, I'll jump in and there are the ridges that have been uploaded in here. The other way you can do it is with these plate boundaries is if you export the topologies. Okay, so in this export option, I can click on add export. And if you go to resolved topologies, this general option, shapefile, of course. Okay, and you should just be able to output just the default here. Let's have a look. So it outputs a whole bunch of things. So it outputs the topology, polygons themselves, and then the boundaries themselves. So if I go to QGIS, 30 million years ago, okay, you'll see those are the topologies, the boundaries themselves. And if I go to the attribute table, it should preserve what feature type it is. So there's the name. Yeah. And then the GPGIM type. And hopefully some of these, yeah, you can see some of these are subduction zones. Okay, subduction zones. And then there are a whole bunch of mid-ocean ridges. The unclassified features are probably things like transforms or more complicated boundaries like that. Okay, so you can definitely explore that a little bit. There are some more advanced ways of extracting just the ridge segments, and you can email me and I can point you to that Python workflow. Okay, so we have essentially covered that import export. So remember, just the key thing is to remember that GPlates stores things in present day coordinates. Okay, and GPlates is happy to work with shape files, happy to read them in, write them out, and so on. So just essentially keep in mind what works best for you. Okay, there was another question about Geo, who asks about the a reference arrow that can be added to look at the actual magnitude. This is a very good question. And if I bring up the arrows again, the question here is essentially like, okay, these arrows are all very nice, right? But like, you know, what is that length? What is that speed? And there's no real easy way of essentially creating a reference one to be visualized. I will talk to John about this again, because I did bring this up many years ago. I suspect that, yeah, it's kind of lower on the priority, but it is important. And Joe, the reason the way I do it is I just always plot it in GMT, because I have all of that symbology functionality, and so just I avoid this problem just by plotting it in GMT. That's really how I do it. And yeah, hopefully in the coming years there'll be more development of the symbology in GPlates. I mean, that is a very high priority actually now. Okay, so we've answered some of those questions in the chat. Mohammed asks a very specific question about rasters. I'm going to write this note for tomorrow, right? I think, or maybe later. So so hang on, let me just see JPEGs. So remind me, Mohammed, about those rasters. When wrong, how do you scale the arrows to be smaller? So you can do it visually here, I think the body right here, or you can in the export, when you've got the velocities here, you can scale here. So if you want, you know, half the size, you can do it here. You can use it. You can do it in GMT as well. So I try not to do that when I export. I leave it as, you know, the actual magnitude, and then I rescale the size using GMT. Okay, Anna asks a really good question, which is the color of the arrows. The color of the arrows is inherited from the plate IDs, right? So if I turn on the coastlines and I mean, where are the static polygons? I'll turn on the static polygons, and you see that the static polygons have all of these different colors, right? And anything that has the same plate ID, so if I'm looking at different parts of the African plate, you can see it's all a plate ID of 701. It has the same color, and there's just a bunch of, you know, default colors in here. You can change the coloring of many of these things, again, through that set draw style. And if you wanted to get really fancy, you can, for example, color by property, and apply a color palette file. So maybe that's something we can discuss on Wednesday. There are, by plate ID, you can color by region instead. It becomes a little bit less jarring. Now, with the colors of the arrows, some of them you'll notice they're black. Okay, and the black arrows are just indicating that the velocities are being read from the deforming networks, and I'll highlight those for you here. Okay, so these mesh points are falling into a deforming network, and they're being triangulated within this deforming network. Now, the reason that's important is that on your plate, your rigid plate polygon, which I'll talk about probably more tomorrow, your plate polygon can be entirely rigid, but if there's some deformation there, well, the velocity is slightly different. And so GPlates preferentially takes the velocity from the deforming topologies. And if you don't want it to do that, well, in many cases, you should be able to just, I think in this case, we can just even disable what happens when I click on disable layer, manage layer, disable layer, okay? And so you can't really see much of a difference except for, let's have a look at the Australia Antarctica example, 802 fixed, okay? And let's go back to the active deformation time. I think I've made the velocities too small. The arrow is too small. Okay, and then if I enable and disable the deforming stuff. Oops, that's the wrong layer. It's now the active deformation. Okay, can you see how that velocity changes slightly? Because here we have more diffuse deformation and velocities. Okay, and then, okay, great. Grace asks a really good question about how you can export the velocities into a shapefile. This is something that's not really that straightforward, but let's just have a look at how I would do it. So let's just say it's at 50 million years ago. I go to velocities. I would still export it into this GMT XY format, right? Single file. Okay, click OK, and I begin the export. Now, the really frustrating thing there, Grace, is there's no easy way of doing that. Let me just, okay, here's the velocity. Oops, I just wanted to open it in a text editor. Okay, one of the things you could do, and I've done this before. It's not the most elegant thing in the world. So if I turn it into, oh, sorry, if I turn it into a text, txt, because Excel, oh God, Excel doesn't seem to like CSVs that are text space delimited. Okay, now, and this is a really good segue to the next point, which is importing your own data. So let's just go to Excel. I want to open. There's a text that's going to complain. Let's just say it is space delimited. Finish. And really, I mean, at this stage, you can just select all and sort by column B, let's say. Right. That allows you to get rid of all these headers. In this case, it was actually fairly straightforward. It was just one set of headers. Headers. And then this is so convoluted. I've done this once before, and you really only want to do it if you have to. But yeah, you can say lon lat. Oops, I think I've spelled lon. You get the point. Azimuth speed plate ID, right? So we can save this out as a CSV or a XLS file, and you can then load that into ArcGIS, and you can, there are ways to apply a symbology, and you apply a rotation to the arrow using the azimuth, and you can apply the scaling using the speed. So I have done it before in ArcGIS. This is generally the trick. So Grace, hopefully that that explains that component. Okay. ITEL asks, how is it possible to export in GMT format or grid the age grid reconstructions of the Central Atlantic at 120, 90, and so on, highlighting the age area distribution of oceanic lithosphere at the time of formation and the extent of continental crust? I hope that we can. Will you be around tomorrow? Because I feel like I'm just going to create myself a list of points, list of questions that we should tackle tomorrow, because that is very specific to the raster stuff that I want to talk about tomorrow. And then there was the other question from, I can't remember what the other question was that we left for tomorrow. Okay, yeah, but that's I tell it's an interesting question, and yeah, it's a little bit advanced. So let's get through some of the more basic stuff today, and then we can delve a little bit deeper tomorrow. Okay, so that's kind of been the crash course of, you know, exporting data, you know, whether it's the velocities or topologies or you know, geometries of coastlines and whatever. The most important question that people ask me is like, well, you know, I've gone to the field, I've collected some fossils, I have a spreadsheet. How do I actually bring it into GPlates? Now, Nicky and Ben will show you how to do that very easily, also with pyGPlates later in the week. So that's very exciting. I'm very excited to attend that. But let me demonstrate how I would do it. And now I've created so many files. You can see how quickly you generate all these exported files. So I'm just going to delete it. Okay. In the little bundle of files that I sent you, I mean, you don't have to follow along with this unless you're really keen. But folder 1 is importing your own data, right? Now, what I've done here is I've downloaded some data from the paleobiology database, right? And it has a bunch of things that you need to keep in mind. So the first thing that I would do is take this spreadsheet, this table, and turn it into a shapefile. Now you can do that with QGIS or ArcGIS fairly quickly. There's no direct way of loading it into GPlates, unfortunately. This is a really good example as well that for your shapefiles, you always need to get rid of things like these headers, okay? So if I delete those, I end up with just the column headers and names, so that's great. Keep in mind that ArcGIS doesn't like column names that have, you know, start with numbers or have spaces or are really long. So, you know, just keep that in mind. Now, the key thing, if you want to display anything in GPlates and attach it to GPlates, it needs to have a number of things. So it has to have at least the latitude and longitude. Okay, so here is the latitude and longitude, and you know, it seems to work easiest with the WGS84, coordinates, geographic coordinates. But I have seen that the GDAL engine, is happy to take in other coordinate systems as long as that coordinate system is not, correctly encoded in the shapefile. Okay, so the minimum you need is the latitude and longitude. And then, of course, if you want to display something in GPlates, well, preferably you'd also have some kind of age constraint. So this is some kind of fossils. I mean, Marissa is here, and others, they can tell me what this is. There's some name. I have no idea what these fossils are. Usually I use a, T-Rex or something. But anyway, here I went got a bit excited. So these are, you can see the ages that are applicable. Okay, so you can import this updated comma separated value file into QGIS or ArcGIS and export out a shapefile. Okay, so I've got a shapefile here. Oh yes, Marissa is keen on those. I think, is it the Cambrian? So yeah, this is a little bit young. So we've got a shapefile that I can now just drag and drop onto GPlates. Now, this is quite useful and important. If you have a field called name or from age and to age, GPlates will automatically map them. But essentially here you can say, well, I want to map the, the accepted name. And you can see how in shapefiles these things get cut off, and it's really, really annoying. But anyway, I think that's accepted name. And then the, well, let's just leave it as that. Okay, so I just want the accepted name. Okay, and I get a bunch of yellow dots across Eurasia. I'm going to make these bigger. Remember that we can go to Tools, Configure Geometry Rendering, and increase the point size to, I don't know, 8 or something like that. Oh, Romana is on the money here. Some cool foraminifera. Excellent. We love forams. I was just ranting before that we're about to hopefully 3D print some forams. That'll be fun. Okay, so what happens is when you import your own data, it is this yellow color, and in most cases it's treated as a plate ID of 0. Okay, so there's no plate ID assigned. Now, and so then nothing moves. It's just fixed in that static present day position. Now you can, if you really wanted to torture yourself, you could go in and say, okay, well, this polygon is South China. It has a plate ID of 602. I can select this point, edit it, and add the plate IDs. But that would be really frustrating and it would take a long time. Thankfully in GPlates it's very easy and quick to do automatically, and that is this what we call feature cookie cutting or assigning the plate IDs. So to do that, you just need to go to Features up at the top, Assign plate IDs. Okay, so Features, Assign plate IDs. You select your cookie cutting layer. Okay, in most cases you will be using what we call the present day static polygons. Okay, so you use the present day static polygons for the cookie cutting. Click Next. You can partition multiple layers, and GPlates is really fast and really efficient in doing that. But let's say here we just want to assign plate IDs for the fossils. Okay, and I click Next. In most cases, you want to do this at the present day. In some rare cases, you might have the paleo positions of fossils which you have to be kind of careful with, but present day is what we're dealing with. And you just want to essentially assign the a plate ID. Okay, and click apply. And you can see that these points have now changed color. They have inherited that plate ID. Okay. And if I start reconstructing and moving things around, those points will move with those tectonic elements. Just a quick note on the static polygons, which we'll talk a little bit more about tomorrow. They're quite useful. But the static polygons are global, and they have a plate ID and an age associated with them, right? So you can cookie cut any data essentially with these polygons, okay? One thing to note here is that different plate tectonic reconstructions have slightly different plate ID systems. So if you've cookie cut your fossils data using, I don't know, the SCOTES model, you can't just then load that shapefile into, you know, the Meredith model, because the plate IDs might be different. So you may have to re-cookie cut, and you might want to save a copy of those files, because you'll notice that the features may actually jump around or not reconstruct properly. So just keep that in mind, that different plate tectonic reconstructions have slightly different plate ID values. Okay, now let's get back to our fossils. Okay, so let's just have a look at those fossils. Okay, I'll hide static polygons and I'll bring back the coastlines. Okay, so these are our fossils. Now, one thing I didn't do was I didn't properly map the ages of those fossils, and I can do that if I go to File, Manage Feature Collections. And then there's a bunch of things you'll see. It's much more exciting now. There's some orange and red in here. In red here, it's saying that I've made a bunch of changes, and you know, I should probably save those. So if I, before I save anything, I can click on this spanner tool, which allows me to go back to that table where I can map the different columns to the GPlates attributes. So for example, the begin time was max MA, and oops, the end time was the min MA. Where's min? Oh my gosh, I'm losing it. I can't see the, oh, here. Okay, and for memory, they were not Cambrian. They were what, like 261, and that's really quite interesting. When I did that, it reset the plate IDs. So that's really interesting. You want to do that first. Okay, well, anyway, let's just, I'll go through cookie cutting again. Partitioning layer of the static polygons. This did happen to me once before, I remember now. Next, apply. All right, so you can see those forams appear when they should in the reconstructions. And you can export them just like we did before in for QGIS or ArcGIS. So Yido asks, is there a way to make the fossil data point bigger? That is a very good question. So if we go to utilities, sorry, tools, configure geometry rendering, we can make that point size, I don't know, let's be radical here. And what's the biggest value? Is it 20? Okay. So we can definitely make it bigger. We can change the coloring. So we can set it to a single color. But unfortunately, we can't assign a picture or a little symbol. That's a known issue. And that's part of the symbology package that's being implemented in the coming months, hopefully. Okay, so let's do a couple of things here, which is let's save these changes. I want to just highlight that I can save these changes. That wasn't happy because I think the coastlines had points and stuff in them. Okay, so the fossils are happy. Okay, now Emily asks, how do we constrain the ages? So if I go to this file, manage feature collections window, this spanner or configure button here next to this Esri shapefile can help me remap what I see in GPlates. So for example, the begin age, you can attach it to any column that has those age constraints. So in this case, begin age is that max MA, so millions of years, and min MA. So keep in mind that GPlates will take in, integer or floating point ages. Okay, it's not going to read in, say, Cretaceous and plot it for you as the Cretaceous. So it does require ages in millions of years ago. Okay. Clicking OK, I can save that again. And one of the things I want to highlight here is that, say, okay, so now I've made some changes to the project, and maybe I don't want to maybe I don't want to muck around with the original project, the data bundle for novice. What I can do, and this is quite important, is go to File, Save Project As, and I can create a new project. And so if I save that somewhere new, so let's just say Workshop, okay. I can open up a new instance of GPlates. I can grab this project file and load it onto GPlates. It will remember all the files that are loaded. It will remember what's shown or hidden. It will remember the coloring, and so it becomes a really nice and easy way of preserving your workspace. Okay, so that's how you deal with projects. You can load in those projects, you can modify and save out the project. Now, keep in mind the way that the project files work, and essentially, I think I'll end on this, and then we can have some questions. The way that the project files work, they're binary files, so you can't easily go and look inside of them. But essentially what they do is they store two things. They store the absolute path to the files and the relative path to the files, right? And it's kind of like a backup, right? If one of those things doesn't work, it will, if it can't find the absolute path, it will use the relative path. What it means is if you're trying to create a GPlates project that you want to transport between different computers, or you want to share as part of a paper, a supplementary section, or share with a colleague, try to have everything in like a self-contained folder, right? You can have nested folders, but you want to have one portable folder, and that project file to be stored in say that top level folder, because those absolute paths won't work if you move it to a new computer, but the relative paths will work. So that's a little bit of a pro tip. It will save you a lot of time and frustration. Again, if you accidentally like save over some files that are in the data bundle for novice, the geodata, it's very easy to recover that pristine thing. I mean, you can just reinstall GPlates from scratch, or you can just download this geodata zip file on its own. Okay, so I mean, we've covered essentially the main things of just kind of getting you started quickly with GPlates, you know, the interface, loading in some of these plate reconstructions, different models, you know, anchoring the different plates, having a look at the velocities, exporting, and some basics of the coloring, layering, and so on. Tomorrow, what we'll do is we'll delve a little bit more into the velocities. We'll look at the kinematics tool. It can be quite useful. It can be useful for teaching, can be useful for research. We'll look at rasters. There was a question from Aitil about rasters, time-dependent rasters, you know, present-day rasters, how we can reconstruct those, re-export them, because GPlates does have a really powerful and really quick engine to rotate rasters. I mean, it all stems from the fact that the lead developer comes from the video gaming industry, so you know he uses the GPU to do all this crazy stuff, which we would never be able to do. So it's really, really cool what it can do. Now, are there any questions? Yeah, so Grace asks a good question about the lat longs when importing the data. So that's a step that you specify in QGIS or ArcGIS, right? Because you load in that CSV into either of those, and then you have to tell QGIS or ArcGIS which columns are the lat longs, right? And as soon as you do that and you save that shapefile, GPlates will know automatically where those lat longs are. Okay. What it does mean is that those lat longs are preserved in the attribute table, and if you edit those values in the attribute table, that won't actually update back to, you know, where the points are, because it's stored somewhere deep in the shapefile system. Yeah. So hang on, there was a yes, Stefan asks for the large igneous provinces. Yeah, so let's have a look at those. So if I go to applications, GPlates, hopefully you can see my screen, geodata, feature collections, and then we have these things. Well, we've got hotspots. Let's just dump in the hotspots as well. Okay, and let's put in the igneous provinces. Okay, now there are two compilations from Whitaker 2015 and Johansson 2018. We call these volcanic provinces because they are not just, you know, the large igneous province plateaus, right? They have a bunch of other things in there as well. Okay, so let's hide the fossils. Okay, so there are those large igneous provinces, or, you know, volcanic provinces. You can export them as shapefiles. You can you know, fill them and change their coloring and so on. Does that answer that question, Stefan? Do you want me to go into any details? Now, okay, continental volcanic arcs. Okay, so that's a different data set. So I haven't actually seen anything easy to use that just, you know, is a compilation of all the continental volcanic arcs, unfortunately. But at least we have these, you know, lips. Sorry, I read your questions from, you know, back to front. Yeah, so Emily, yeah, it would be really good. Maybe we can do a kind of collective brainstorming and see if there's some volcanics that are age coded. I know EarthChem has a database, but I thought that those were mainly like basalts and so on. But maybe EarthChem has a bunch of things. And I know that not all of the samples in EarthChem have an age associated with them. So we can definitely dig around together. Yeah, so Karen asks about the configured geometry rendering. Unfortunately, it applies to all the layers, and that's the frustration at the moment, is that the symbology is so limited. But that is coming in a future release of GPlates. That symbology is top priority. Including subduction zone teeth, which I have been complaining about for 10 years. So hopefully by Christmas, we'll have subduction zone teeth. And like you say, Karen, being able to control the different, thicknesses of lines for different layers, different symbols, and also have them time dependent, maybe like a color palette lookup table. So Stefan, you bring up Cowan Lee. That's a good question. We never digitized those like in GPlates. We did extract the time series. We did kind of create our own volcanic arcs using our recent paper. I can send it to you, which is essentially what it does. It looks at the subduction zones and then finds the continents that it's interacting with. Let me just have a quick look if I can bring it up. Is it 2021? PD 2022? I have no idea. Carbonate, subduction. Yeah, so we were looking at subduction carbonate platform interactions, and we did at some stage, we were comparing the continental arc lengths. So this is the Cowan Lee arc lengths. This is our arc lengths that are implied by the reconstructions, but we never essentially in this process, we never actually output the GPlates visualization friendly arc. So that's something I can try to hack and output. Okay. Oh, and Wenrong, yeah, okay. And Wenrong is here, of course. So, but if Wenrong, if they're in discrete time steps, and I believe you use the Scotese model, you can attach it to the Scotese model and create a more continuous arc. So this is great. We're talking. We can solve some of these problems together. And Stefan's interested in the Cretaceous. So one time step, we can try to fix this in the GPlates workshop. Love it. There's research happening live as we speak. Yeah. So when wrong, we have higher arc lengths because we just assume that anywhere that you have an overriding, continental polygon, that you are creating a volcanic arc. But that's also not quite true, because parts of the Greece and Turkey, there's subduction, right? But there's not a very significant arc system, so I think we kind of overestimate. Maybe some of the geological record underestimates it, because maybe some of those volcanic arcs have been lost to erosion and so on. So it's probably somewhere in between. Okay, great. Any other questions, team? Excellent. So we've covered a lot. I apologize if we jumped around a little bit, but it's always nice to be a little bit more organic and flexible and address the things that people actually need and use. But we did cover the basics. Tomorrow, we'll look more at rasters and fun things, particularly for making like figures and making hopefully animations and bringing in your own rasters, exporting your rasters and so on. Okay, wonderful. I will, again, I'm sorry, I will email this Zoom recording around to everybody, because there's a lot of people who said that they couldn't come today, but they want to come tomorrow and they want to be able to catch up. So have a great remainder of the day. Have a great sleep for those of you in Patagonia or wherever else. And thanks so much for coming along. All right, bye team. See ya.